Hello, Mr. Ryan, right? Okay, so we have an array of integers. Just look at these three examples. We're given this array with positive integers, for simplicity. And we're given an x. Okay, and then I'm going to write an answer and you guess. If you can guess it out, 5 more minutes bonus. The answer for this is 2. The answer for this is...
Do we both get it?
Yes, of course. The answer for that...
teamwork. Right?
Yeah, teamwork. Okay, so what's the answer for that?
Wait.
Wait, this answer is -1. This answer is...
Okay, this is probably... There's probably like this...
Wait, okay.
A detail about a few array of numbers, and this one doesn't have it.
Okay, let's say this is 3, okay? Okay?
You said let's say.
Yeah, I forgot. I think this is not a correct example, but anyway, I modified it.
How's that fair? 1 plus 1 is 2. Yeah, how's that fair?
That's fair. Okay, so this...
Because we only get 2 correct answers.
Okay, so if you... No. This... What do you mean correct answer?
1 plus 1 is 2.
If you can reason that why this is the input, right? This is the input. This is the input. If the output you can reason, and it's fine. 5 minutes more.
1 plus 1 is 2. 4 minus 2 is 2.
What's this x here?
Yeah. Maybe
X here.
maybe 1, 4, 2, 3. I don't know. And then.
Okay, this is -1.
And then see, look, you can't make anything with because these are less. But this.
Yeah, why this is 2? Why this is 3? You're quite close. Yes, you can't make anything up to 4.
Yeah.
Okay.
Because this is smaller than all of those.
Okay, so you can get that right 2 minutes.
Yeah, we already got this one.
2 minutes, okay?
We already got it right.
Okay. How about if say this 2, 3 is the numbers of numbers? So what can you get?
8 is 3 numbers less than that, right? Or less than half or something. And then this, and then there's 2 numbers less than half of that.
Quite close, okay? But I'll give you 4 minutes. Is that fair?
No.
Okay.
You said 5 minutes.
No, but you're not getting it all right. 4 minutes each, okay?
2
Okay,
battles.
sit down. Sorry?
2 battles then. Yes. 2 battles then.
2 battles.
In probably from that.
Okay, sit down. That's fine.
Okay. Plus another 30 minutes is 50 minutes.
No. That's too much, okay? So we're given this array. For each operation, you can remove the number from left or the right. For example, in this case, you can remove 1 and you can remove 3. And we want to reduce this x to 0. So in this first example, we can remove 1 and we can remove 3. You have to remove it one by one. So for first example, we remove the 3 and then we remove the 2.
Yeah,
so
that's what I was saying.
Yeah, okay?
I literally said 2 and 3 and 1 and 4. Yeah.
No, you can only remove element from the leftmost and rightmost. Okay? So you remove 3, then you can remove 2. But if without removing 3, you can remove 2. That's what I'm saying. Okay? So for the second example, it's 3 numbers because it's removing the 3, removing the 3, and removing the 2. Okay? And the third example, obviously, you can make a target for. Makes sense? Okay, so we're given an array of integers, positive integers for simplicity. For each operation, you can do 2 things. Remove the first on the left or remove the last on the right. Okay? So we want to reduce the x to 0. So we want to find out the minimum number of operations. Right? A few weeks ago we talked about minimum number of operations to bring n to 0. For each operation we can add or subtract any power of 2, right? That is similar to this question, but this one the rules are different, right? You can only remove 1 integer from the leftmost or rightmost.
2 pointer?
2 pointer, yes. Why is it 2 pointer?
Because you have 2 pointers.
Why is it 2 pointer?
Because you have 2 pointers. So you can remove.
Yes, because that's all very obvious, right? We
Yeah,
cannot do
I
choice.
said it before though.
Yeah, okay. So
you asked why 2
How
pointers.
do we
I
apply
said,
these 2
because
pointers?
it's 2 pointers. And then you asked the same question and I said it's 2 pointers.
how do we apply 2 pointers?
Yeah, you put put two pointers.
Okay.
You remove it, numbers with it.
So-
and then you move the right, left.
So there are only two possibilities at each step, right? So we just have to check which one is shorter, which one is quicker to bring down the x. Alright? There are other algorithms to solve this. Today, let's just solve this using this 2-pointer. So yes, you're right. So if this is array A, so each step we can do two things. We can either take one on the left or we can take one on the right, because that's only two possibilities, right? Okay, so we can use this f, let's say f. At the beginning, we have these 2 pointers, L and R, and then this is the current sum, x, okay? So this function takes 3 parameters. The left, the pointer left, the right, the pointer right, the x, the current sum. L left at the beginning points to the first element, the right points to the last element, and this is the current sum. So there are only 2 possibilities, right? 2 possibilities. So which possibility? I write one and you write another one, okay? So f L plus 1 R x minus, if this is array A. Okay, so what's the other one? So L plus 1.
R plus 1.
So f.
L x minus A L.
What's this? That's L, right? Because if we don't remove the leftmost, the left pointer stays the same. The right, which is
R plus 1.
R is here, plus 1 is
Minus
here.
1!
Minus 1, okay? X and X. What? Why is it plus? Come on, you're not guessing. X what?
No, because you haven't even gave us anything, so we're guessing. No, we're using logic, so we're just guessing.
X
I
what?
think it's plus.
1 minute.
Minus.
Minus.
Okay.
Okay, 1
A.
minute.
What was it?
Oh, 51 minutes.
No. Okay,
Yes,
let's not go
Dad.
back. Okay, so there are only 2 choices, right? This is very obvious. So is it? Yeah? Yes?
Not really. You didn't give us, you didn't tell us anything about that though.
Okay, so this is 2 possibilities. We just have to pick the minimum of it, right? Minimum of it, and then plus 1. Alright? Because it needs one more operation. Alright?
Yeah,
Okay, so let's implement this.
That's not.
And then you need to tell me how do we analyze the time complexity. Define, okay? So if x equal 0, then we return 0, right? So if we are able to bring down the x to 0, then return 0. Or if we already given a sum which is 0, then you don't need to remove anything because it's already 0.
yeah.
Right? And if the left pointer is bigger than the right pointer, or x smaller than 0, right? If the left crosses the right, what happened? Or if the sum is less than 0, that means it's impossible, right? So in this case, we return infinity to indicate this is impossible. Okay, infinity, because we are minimizing. Okay, because we are minimizing these 2 roots. Right? If one of them is infinity, then they will not be taken. Does it make sense?
Yeah,
If the left pointer cross the right pointer, right? The left should be on the left of the right, right? If the left cross the right pointer, it's invalid. Or the sum is less than 0. It means that
Why don't
it's
return,
impossible.
Why not return minus 1?
good question, because we are finding the minimum here. Okay, so infinity here, but we're going to check. We don't correct it as minus 1. So if the answer would be just this one, right? Okay, let 2 recursion. And
Ding
Ding.
And
dong.
now actually answer, right? Not plus 1 because infinity can't be plus 1, right? Answer equals that. And if answer is infinity,
La 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 la.
if the answer is infinity, then we return answer, right? Otherwise, we return answer plus 1. Okay. This is just to avoid we are plusing the we are adding. Okay, you understand what that is saying? Yeah. We don't want to add 1.
Do you say plusing in Microsoft?
Okay. In Python, infinity plus 1, this doesn't work, okay? Because infinity is infinity. It's a concept. You can't plus 1 to infinity, right?
Infinity plus 1
Ah!
equals infinity. infinity plus 1 is infinity. And also,
Yeah, very good. Yeah, infinity plus 1 is actually infinity, but yeah, it's
is the limit. Well, infinity is not really a number.
because infinity is not a real
And
number, so you
infinity-
can plus 1 on infinity.
Infinity is
Add
a Pringles symbol.
Okay.
Add one.
Infinity is Pringles.
Okay. Okay. So after this, we call this function, right? And if this function,
It's Pringles in a certain angle, not necessarily. If you look at it from bird's eye view, then it's probably a potato, and then or 0, and then if you look at it when it's like twisted, and then it's
okay. Ryan, you say why not minus 1? Here we do the minus 1. So if it's infinity, it means that both ways, neither of these will
but
find
you're
it.
saying
So then
not-
we return minus 1.
Why not? But he was talking about before,
Yeah.
but he was saying why not for that one, and you already answered it.
Okay.
La.
Okay.
I am sitting.
Good. Okay. Bless you.
Yeah.
Let me repeat, okay? So this is the recursion, right? We're using 2 pointers, the left, right, and the current sum. If the current sum is 0, great, we find it. If the left pointer at any point crosses the right pointer, or the sum becomes negative, it means that we are reaching the end. We can't find any solution beyond this point, so we return infinity. There are only 2 possibilities at each path, right? So it's a binary tree, right? It's a binary tree actually. Recursion calling spawning into 2 branches. If we want to get the minimum of this, right? We got the minimum. If it's minus 1, then it will be taken because minus 1 is pretty minimum, right? Okay. So we want to make it infinity. So the minimum of infinity and another number, that will be another number. The value will be another number. Okay. Okay. Okay, and then if answer equals infinity, then we just return infinity. Otherwise, we need to plus 1 to the number, add 1 to the number, because we don't want to add
3
1.
times.
We don't want to add 1 to the infinity. We're calling this function with the 0, which is the leftmost boundary, the length of A, the rightmost boundary. Index start with 0, so then minus 1 and current sum. And if it returns infinity, it means that we don't find such possible solutions to reduce the number x to 0 and we return minus 1. Okay, otherwise we return the answer. Okay, so there's one thing missing here. There's one thing missing here. The recursion, right? What's missing?
Cash.
Yeah, we can minimize these, right? Cache, the left, the right, and the sum. Okay, so it's still not very optimal. This solution is not very optimal. The next lesson we're going to talk about the optimal solution, which is the actual 2 pointer. This is kind of like recursion. Okay, recursion. It's 2 pointer, but it's not the optimum 2 pointer. We're going to talk about the sliding window. So okay, so right, this one, right? 1, 1, 2, 3, 4, and then if this is 7. Actually, let's make it 6, okay? We want to reduce this array to reduce the 6 by taking the number from left to right. What's the opposite of this question? What's the opposite? If I take the 4, take the 1, take the 1, what's left?
2 and 3.
2 and 3, okay? So what's the opposite? What's the total sum of this? What's the total sum? 1, 1, 2, 3, 4. You know you can calculate this, the 11, yeah?
11.
Okay, 11. The total sum is 11. I want to take a 6. What's the remaining? 5. Okay, so what's this question? If we want to,
What are the sum of the numbers?
yeah, we want to minimize the number taken, so we want to maximize the number remaining. Is it the same? Is it equivalent? I want to minimize the numbers taken. Is it equivalent to I want to maximize the number remaining? Think, big brain, think. Is it the same? Okay, we talk about this.
Yeah, but
We'll cover this in the next lesson.
What if these 2 were like swapped?
4 and 3.
With a bad pen.
Very good. 4 and 3. So can we make it?
No.
Yeah, we cannot make it, right? But this is the same. Total sum is 11. The number is 6, so the remaining should be 5. We want to find the maximum subarray, which is 5. We can't find it, right? Can we find it? We can't,
Yes.
right? Okay. Okay. So the cache. Final last thing is the what's the time complexity for this one? Can you guess? So if there are n numbers, So let's look at the first two, L and R. What's the range of L?
L.
There are n possibilities, right? What's the range of R? N. So this is O n squared, right? Because the L and R, the left pointer and right pointer, that's O n squared quadratic. But this X, the sum could be very big, right? The sum could be very big, so this is not very optimum. And the time complexity will be O n squared times the sum, the biggest sum. So the sum, let's say the big S, okay? This could be very big, S could be very big, so this is not very optimum. And this will be very slow and sometimes out of memory. We need more memory to cache all the states. Okay? Remember this search tree, F0, if R is 10, for example, and if this is 100, the left will be F1, 10, and 100 minus A0, right? The right will be F0, 9, 100 minus A9, okay? So every time the binary tree spawns into two kids, which may overlap. That's why we need a cache. We need a cache to prevent the same state has been calculated again and again. Total number of states could be very huge, n squared times s. So this is not very optimal. We're going to talk about this sliding window, the opposite. Sometimes the question may seem hard, difficult, but if we reverse the thinking, right, like this is a perfect example of reverse. Yeah, because the question is asking what's the minimum number of operations to take numbers from left to the right to bring down the x to 0, and the opposite is easier. What's the maximum remaining sum subarray? Then that's easier. That seems easier, right? These two problems, same answer, but the opposite is easier to tackle. Am I right? Is it easier to tackle?
Yeah.
Okay, so what have you learned today? That's it. What have you learned today?
Oh.
Final part. Final part. What have you learned today?
Numbers. We have a list of numbers.
Yeah.
Then we use the 2 pointers, deleting left and right parts.
Okay, so it's a teamwork. Ryan, you describe to me what is the problem, and Eric, you say what's the situation, what's the solution, or you want to solve.
The problem is that we have numbers and we have x, and then the target is x, and then we just we can sort of like delete the leftmost number over rightmost
Number, yeah.
Yeah.
So we want to minimize the number of operations to bring this x to 0. And this is kind of like double NDQ, right? So every time we can take the numbers from the left or the right. Okay? The solution is
2 pointers.
2 pointers. So basically there are two situations. Either we take the number from the left or we take the number from the right and we just compare which one is the shortest. And this is recursion, right? So every time we can take two numbers, we have two solutions. Take one on the left and take the one on the right. And then we bring down the x to 0. Okay, so that time complexity in theory is 2 to the power of n. Because every iteration you have two choices. But we have added optimization, which is when the left crosses the right, or when the sum becomes negative, there's no point to continue. Am I right? Yeah. If the sum is positive, if the sum is already become negative, that means that there's no point to continue searching, right? Because you keep subtracting numbers from the negative, you become even negative. You will never become 0 again. Okay, all the numbers are positive. Okay, that's it for today. Bye bye. Bye bye.
Bye.
Bye bye.